Hi, and welcome to today's talk about the generation of synthetic tabular data in the medical domain. First, I would like to speak about why it would be great to have in general more medical data. So, it would help to discover faster disease patterns and treatment options, especially in cases where we currently don't have much data, and therefore it would help to improve medical research. But also it would be great for reducing the bias in medical research because usually the data we have does not represent all the countries and all the different ethnicities equally. So if we had more data from countries that we currently don't have, that would be so great. It would also help with machine learning in medicine because how it currently works is that a company teams up with one or a few hospitals to develop an AI algorithm, let's say for the diagnosis of a certain disease. And usually it works very good in those clinics, but does not generalize well to other clinics when they try to roll it out. And for that, it would be great to have more training data just to help the model generalize better and probably be better usable in also other hospitals. Last but not least, also for startups, it would be amazing to have a lot of publicly available data because usually they team up with a hospital, but it takes forever to get first the data. And that would make it just the starting point of a project way easier. So after hearing all those great things, you might think to yourself, so why is actually not more data publicly available? So besides also ethical considerations, because it's such a sensitive data. You would not really want your electronic health records out there with your name and everything, right? So you would want them to be kind of very privately. There are legal restrictions that also prohibit the sharing of such data. However, they do not actually apply to fully anonymized data. So you might think to yourself, great, so we just need to anonymize the data and then we can publish it and everything is great. Yes, actually kind of like that, but just anonymization is not as easy as you might think. And there have been some failures in the past, and I just want to quickly show you two. The first case is kind of old, 97. It's about Massachusetts. And basically in 97, 135,000 records were released. And they believed that those records were completely safe because they removed all the names, addresses. But what they kind of kept inside was the date of birth, zip code, and sex. That was not secure enough because Latina Sweeney, at that time still a student, actually could identify the governor of that time. For that, she bought some voter records for just $20. I'm not sure if it's still possible in the US, but basically those voter records, they had the full names of everyone, zip codes and sex. So she could combine the two datasets using that. And for William Weld, who at that time was a governor, there was exactly just one person with the same date of birth and zip code. So it was him. She actually mailed his records to him just to show that, she got it. So that was a big failure. Another one that I want to speak about that is less obvious than the first one is of Netflix. In 2006, Netflix started, it was called the Netflix Prize, basically a machine learning competition where it wanted to improve its recommendation system. And for that, there was data of 500,000 subscribers included. And the data included ratings, basically the timestamp of the ratings and basically IDs of the users, but not the same IDs as you would see in Netflix. So they didn't think it's problematic. However, what researchers did is they combined this data, so it's again a linkage attack, with IMDb data, which is a public database where everyone can leave also reviews on movies. And they found out that there were kind of a lot of people who used both and left the same ratings kind of there at kind of same-ish times, so they could identify the people. And the problem is that in IMDb, people sometimes use their real names. And now you might think, okay, but where's the problem? Because those were the movies that they rated publicly, so they wanted it to be seen, right? Might be the case, but there were also movies in Netflix that they rated that they did not rate on IMDb, and those could be the problematic ones, because at least according to the authors, it could be something about sexual orientations, specific movies that they rated on Netflix but would not want everyone to know, or political documentary. So yeah, kind of stuff like that. As we have seen in the previous examples, there's a risk of re-identification. So what could we do to reduce this risk and still be able to publish data? One possibility is to look at synthetic data instead. So instead of publishing the real data directly, we could train a generative network on it, which learns the distributions and correlations of the real data, sample from it, and because we are sampling from distributions, we can generate way more or way less data than our original cohort. And this data we could maybe share. Because we are sampling from distributions, we do not actually have this link of a synthetic patient to exactly one real patient, which makes the whole re-identification way more unlikely. Let's have a quick look at such a table. Of course, this is just a minimalistic example, but this is still a typical patient table where each row represents exactly one patient and each column represents an attribute of that patient. We have here sex, which is categorical. We have age, which is numerical feature. We also have, for example, TP53 and NPM1 mutations, which are binary, meaning 1 there is a mutation and 0 there's no mutation. And we have a continuous feature here, overall survival time, or in short, OSTM. Let's have a look at generative models that can be used for this task. Usually they are coming from the image generation domain, and so is also the case of the two models I want to show that are the most common ones. The first one being the Variational Autoencoder. You might have already heard of it because there's a whole lecture on it on this channel. So if you're interested, have a look at it. The intuition here is that we have our picture on the left, our original input. Then we have a neural network, which is an encoder. And as you can see in the shape, it starts basically with an input of the original data, but it brings it to a lower dimensional space, which is called the latent space. Basically, through this encoder network, our picture is transformed to to a representation in that latent space, from which then the decoder, which you can see, starts small and becomes as big as the real data was. And this decoder learns to reconstruct the image from that lower dimensional latent space. And in variational autoencoders, the latent space is learned to be normally distributed. This is important because once we remove that encoder, we can actually sample from a normal distribution, and then the decoder can generate out of this a synthetic image. Lei Shu and his colleagues found that it works also for tabular data. However, some adjustment need to be done. In their experiments, they determined that first it makes sense to transform continuous variables into a different representation. As they observed, a lot of continuous variables have multiple modes, as you can see here. So they determine those modes by fitting variational Gaussian mixture model to that, and you can see they determined here in this case 3 modes. And basically the beta that you see here is just a chosen mode for a specific value of one continuous variable, and then alpha is just a normalization using basically this mode. And this is basically this part of the input, and these are just the one-hot encoded categorical features. And then in general it works the same as this one, the same idea. However, the encoder and decoder networks are also different, because here the encoder is usually a CNN, and here the encoder is just a multi-layer perceptron. Let's have a look at a different architecture, and this one is by far the most used for synthetic tabular data generation, and it's called Generative Adversarial Networks. Again, it comes from the image generation domain, and it consists of 2 neural networks. One is the generator, one is the discriminator, and their loss is combined. The generator tries to generate synthetic data, and discriminator always gets the real data and the synthetic samples and decides which one is true and which one is false. So let's have an example from the image domain, which is kind of commonly used. So we have our generator network represented through a criminal who tries to generate fake money. And then we have the discriminator network here shown as a policeman, which gets basically the fake money, but also has real money. And now he kind of looks at both and decides which of them is real. And by that, he actually learns to better distinguish real from fake data. However, the generator, so this guy is a criminal, let's assume he has some kind of, I don't know, webcam or something attached somewhere where he can see the policeman making the decisions. And that's how he learns, basically through backpropagation, but he learns to better generate fake money. So in the beginning, kind of might look like this, not even close to similar, and with a lot of trial and error, the generator becomes better at representing the real distribution and therefore the real money. In general, it works the same for tabular data as well, and we can see that the same representation of tabular data is used as for variational autoencoder. However, we can see that there's something extra here, and this is a conditional vector that is used here. The reason for that is that in tabular data there are a lot of highly imbalanced categorical variables, and especially in the medical field, like rare diseases, for example. And if we do not condition our generator, we have the problem that the generator learns to generate the most common values and probably ignoring a lot of rare values. And to make the generator not ignore this, the authors came up here with a conditional vector which first randomly selects a categorical variable, and then in this categorical variable the value is chosen with the log frequency of the original data. And then we have basically one value for one categorical variable, which is the one-hot encoded vector, and this is given to the generator. And this forces the generator to generate exactly this value for this variable. And to make the discriminator, or in this case the critic, learn this, he gets always the real sample which also fulfills this condition. And this helps the GAN model to learn also more rare categories and not just the common ones. Since the introduction of CT-GAN, there were several improved approaches proposed. One of them is CTAP-GAN Plus. The first thing it improved on is the feature encoding. Before, continuous variables were always treated as they had multiple modes, but this is not always the case in real-world data. So here's a smarter approach where they automatically test each column for its specific type, and based on that they do some transformations. So for example, if it is a long tail distribution, then a logarithmic transformation is applied. If they detect that there are multiple modes, then it's treated the same as in CT-GAN, and otherwise some other transformation is applied. Additionally, to improve the performance of the synthetic data on a machine learning downstream task, they included a classifier or a regressor inside their model. And additionally, to improve also the distribution matching with the real data, they introduced information loss, which is basically computing the differences of means and standard deviation for continuous variables. So after we had now a look at different architectures, how do we actually know if the data generated by any of them is any good? How do we judge that? So first of all, there's not exactly an agreement on which specific evaluation metrics to use, but usually multiple metrics are used in conjunction. And roughly they can be divided in three categories. The first one is resemblance. How closely can I replicate my real data? For that, we usually compare distributions, individual ones, but also joint distributions. We look at correlation between variables. We can also, for example, train a machine learning model that tries to differentiate between real and synthetic data, so kind of discriminator. And in the best case, we would get an accuracy of 0.5, which would mean that our model cannot differentiate between the two. Next, we also have utility. So how good is the synthetic data actually for a specific task? A lot of times this task is machine learning prediction, and for that we basically want to predict a specific column, and then we are using synthetic data to train our model and evaluate it on the real test set. And then we compare this to a machine learning model trained on the real training data and compared again to the test data. And it would be good if the difference is minimal. However, there could be also other utility metrics. For example, if we are looking at some specific medical analysis, in case of clinical trials, we would look, for example, at Kaplan-Meier curves and to see if, for example, the survival has a similar curve. And last but not least, we have privacy. For that, we can look, for example, at the attribute inference attacks. The idea here is that we have some certain knowledge about a patient from which we know that he was part of the training set. And now the idea is we have just like some partial knowledge about him. For example, we know that it's, let's say, it's a 91-year-old male patient. And can I infer other sensitive knowledge about this patient given the knowledge I already have? And that might be the case if that real patient was an outlier in the real data set, because it can be that if I look at the synthetic data, I have exactly one patient who is kind of in a similar range of, let's say, 91 years old, while all the others are like 80. Could be. And then if kind of those attributes match that I have from him, they could make sure basically that whatever other attributes he has, that they match. So, and those could be sensitive ones. For example, does this person have a specific disease or something? Another attack would be the membership inference attack. Here the idea is, was this particular individual in the training set? This can be problematic in cases where just a participation in the data set is kind of already sensitive. For example, maybe that study that we are trying to synthesize is all about people with AIDS. So that would mean if the patient is inside, then we know that the patient has AIDS. And this is usually done with distance to the closest record. So we are kind of computing distance to all the records and then define a threshold. And if it's under that threshold, we assume that this patient might have been in the training set. So after we have heard now something about evaluation, forgot to say one thing. In general, there's a trade-off between privacy, utility, and resemblance. So if you increase the privacy, you get worse in the other two. However, I just actually wanted to explain more realistically how does synthetic data generation kind of work. So we first have data, then we actually pre-process data. We didn't speak about it, but we would remove, for example, identifiers. We would remove redundant variables, impute missing variables, or also transform variables. Then we would select multiple generative models. Why would we not select just one? Because usually we do not know in advance which one gonna perform the best, and at least currently there is not a single one beats all models for all use cases. Then we would also select our evaluation metrics. And then we didn't speak about it, but actually all those generative models, they work better with optimal hyperparameters. So hyperparameter optimization makes sense. And then once we obtain those hyperparameters, we can train our generative models. And then we have multiple fitted generative models. And we would do that multiple times again. Why not a single time? Because there's a difference in quality depending on the random seeds that we use for training. So if our goal is just to publish the data, then we can train a few more models. And once again, we can sample multiple times from each model because there's also a difference in quality for each sample. Then we would actually remove medically implausible data, for example, pregnant men, if we have something like this, which is going to be different for every single use case. And for that, kind of we require doctors. Then we would evaluate all those synthetic data sets and kind of pre-select the best, let's say, case synthetic data sets given our metrics. And then we would actually give it to a doctor that we cooperate with, and he would do some additional medical analysis. And then we would select the final synthetic data set or data sets, depends on our use case. Then we would actually create a document where we document all the metrics and tests we have performed. So it's clear for what the data has been tested and for what maybe not. And then we could maybe publish the data. One important thing to say is this whole process is iterative, because it seems here like, oh, it's always like this. It kind of depends. If we at certain points see that the quality is not as good as we wanted it to be, then we might need to go back to the pre-processing step, for example. It could be, for example, that when we try to remove medically implausible data, we see that we removed 80% of the data, then something is wrong, and we need maybe to think about different transformation steps in pre-processing or something. Or it could also be that we give the data to the doctor and then he looks at it, compares it to the real data for his medical analysis, and then says, this is not even closely as good as we needed, and then we are back to the beginning. Yeah, that was kind of a short introduction to the topic. If you have any questions, now would be the time to ask them. Thank you very much for your attention.